In the last segment, what we did is we took a look at methods by which we can calculate the properties of gas mixtures, be it internal energy, enthalpy, or entropy. What we're now going to do is we're going to work an example problem, and that will enable us to apply some of these different ideas in terms of coming up with a solution. So I'll begin by writing out the problem statement, and then we'll proceed through the problem. So there's our problem statement. What we have is an adiabatic mixing chamber, and we have two fluid streams coming in. One is ethane, and we're told that it's at 20 degrees C and 200 kPa, and the other gas stream, methane, at 45 degrees C and 200 kPa. We're given the flow rates, the mass flow rate of both of them, and we're told to find the mixture temperature. So that would be the fluid stream leaving, as well as the rate of entropy generation during the process in units of kilowatts per Kelvin. So that's the problem statement. What we'll begin by doing is writing out the information that we know, and then we'll proceed through the solution. So those are the things that we know. What I've done is I've gone into the back of the book and I've pulled out the values for the gas constant for both ethane and methane, specific heat, as well as molar mass. Now, the temperature change here is not that significant. We're going from 20 to 45 degrees C, so the mixture coming out is going to be somewhere between those two, and consequently, this would be one where the specific heats are not going to change that significantly, and consequently we can make approximations there. We don't have to do the exact analysis where you'd have large temperature swings. So what we're going to do, we're going to begin. I'll write out a schematic of what this problem might look like. It's basically quite simple. It's just a mixing chamber. So we have a mass flow rate of ethane coming in, mass flow rate of methane, and then leaving we have the mass flow rate of our mixture. And what we're going to do, we'll start by applying the first law of thermodynamics to this. It is a steady flow process, but it does have multiple inputs and one output. So let's write out the first law. Now we can neglect kinetic and potential energy. They're not changing. We have no information on them, so we neglect those. We were told that it was an adiabatic mixing chamber. Mixing chambers do no work, so those two disappear. And what we're left with then it's going to be the mass flow rate of either ethane or methane multiplied by the change in enthalpy of those two fluid streams. So this is where we will be making an approximation in terms of the specific heats for the enthalpy change. And in this equation, we know everything with the exception of the exit temperature for the two fluid streams. And so what we can do now is we can insert all of the known numbers and then calculate for TE. So that is what we determined to be the exit temperature, which addresses the first part of the question. And so you can see one of our fluid streams was coming in at 20 degrees and the other was at, what were they? They were, one was at 20 and the other was at 45, and so we come out at around 30 degrees C, which is pretty much in the middle there. So what we'll do in the next part, taking a look back here, they want us to calculate, so we got the mixture temperature. The next part is the entropy generation. That'll take a little bit more because we got to worry about entropy change for a gas mixture. But that is what we will look at in the next segment.